So our next speaker is one of our organizers, Prabha Mandyam, and as soon as we have room for her to come up to the podium, we'll start.
Thank you, Charlie. I hope I'm audible. Okay. So I'm going to be talking about some recent work done with Shom Bandyopadhyay, who just gave the previous talk, Bill Wouters and Marcus Grassel. So for details, you can of course look into our somewhat recent archive posting. So I'm going to be talking about construction of unextendable sets of mutually unbiased bases from Pauli classes. So I'll of course define what I mean by unextendable sets and what I mean by Pauli classes as well. So let me begin. So this is going to be the outline of the talk. I'll give a brief overview of mutually unbiased bases, an example of a particular construction of mutually unbiased bases, which we will use in, which we will heavily make use of in our construction of unextendable sets. I will also try to motivate why mutually unbiased bases are at the very heart of a lot of quantum information processing tasks. So the particular construction will be on obtaining mutually unbiased bases from what are called maximal commuting classes of Pauli operators, which I'll define more precisely as we go along. Then I'll tell you about our construction of unextendable sets of mutually unbiased bases, particularly for 2-qubit and 3-qubit systems. Unfortunately, we only have a conjecture for n-qubit systems based on the construction that we have for 2 and 3 qubits. And then I'll also talk about why unextendable sets of such bases are also interesting. In particular, I'll touch upon two interesting properties that we observe. One which has to do with saturating an entropic uncertainty relation. With this property has the potential to be of much use in quantum cryptography settings. And another interesting property, which may in fact have some consequences for foundations, which is on obtaining state-independent proofs of the Cochin-Specker theorem, which Professor Guru Prasad Kar talked about yesterday in his tutorials. So what are mutually unbiased bases? So consider a d-dimensional system, then any two orthonormal bases are said to be mutually unbiased if every pair of vectors AI and BI satisfy this property. So what is the sort of implication of this mathematical definition? The implication is that imagine you prepare this d-dimensional system in an eigenstate of one of these bases. Say you prepare the system in an eigenstate of basis A. Now if you measure this system in an eigenstate of basis B, then all outcomes will be equally probable. So these are bases which are completely unbiased with respect to each other. If you're in one basis, then if you try to obtain information in another basis, then you essentially have no information. All outcomes become equally probable. So a set of such bases would be called a set of mutually unbiased bases. It just means that so I use B1, B2, etc. to refer to bases. So if every pair is unbiased, then we say this is a set of mutually unbiased bases. So we of course have very simple examples to understand this property. So for example, of course the eigenbases of X and Z themselves are mutually unbiased. This is for a single qubit. So the basis A would then just be 0, 1, say the eigenstates of Z, and the basis B would just be the eigenbasis of X. So I just denote the eigenstates as plus and minus. Then it's easy to check that these vectors satisfy this unbiasedness property. So of course one can, another simple generalization which is often used, which was sort of used in the early days and continues to occupy a prominent position in quantum cryptographic settings, are these so-called computational bases and Hadamard bases. So I think even Umesh referred to them in his setting of device independence QKD. So the computational basis is simply the eigenbasis of, you can think of it as just I tensor K, and H being the Hadamard operator, you can think of the eigenbases of H tensor K, and these eigenbases also satisfy this property. So this is just to tell you what MUBs are, and just to give you some idea of some examples to give you a better picture of what I mean by mutual unbiasedness. So now, do such bases exist in all dimensions, and how many such bases exist in higher dimensions? So the first important result in this was probably due to Wouters and Fields in '89, who showed that if you are in prime power dimensions, then they could provide an explicit construction of D+1 such bases using generalized Pauli operators, which I'll just define shortly. Interestingly, it was shown by Schoom and his collaborators that the maximum number of such bases in dimension D is in fact D+1. So the maximum number of MUBs that can exist in any in dimension D is D+1. In composite dimensions, smaller sets of MUBs have been constructed. For example, constructions are known using mutually orthogonal Latin squares, and so I was talking about these generalized Pauli operators. So this X and Z are essentially what I mean by the generalized Pauli operators. So these are essentially the generators of the discrete Weil-Heisenberg group in D dimensions. So this you can think of as a translation operator, this you can think of as a phase operator, and what Grassel showed in 2004 is that for any finite D, there always exist three mutually unbiased bases, namely the eigenbases of X, the eigenbases of Z, and the eigenbases of the product of X and Z. And the problem of actually extending this to, say, the maximum that we know can exist has been a really hard problem. So much so that the question of whether there exists such a complete set, by complete I will just mean D+1 basis, the question of whether there exists a complete set of MUBs for non-prime power dimensions still remains an important unresolved question. We don't even know whether there exist 7 mutually unbiased bases in dimension 6, for example. So why are MUBs important? So here's a couple of reasons why we should be interested in mutually unbiased bases. So first and foremost, MUBs form a minimal and optimal set of orthogonal measurements for quantum state tomography. This is easy to see because to specify any general d-dimensional density matrix, you need d square minus 1 real parameters. Measurement in each basis is going to give us d minus 1 independent probabilities, which means we need d+1 distinct basis sets in order to obtain d squared minus 1 independent probabilities. Now, another interesting property of mutually unbiased bases, which is being used a lot in recent times, is the fact that they are also the measurement bases that are most incompatible. What do I mean by incompatible? So here incompatible will be understood as quantified by entropic uncertainty relations. So what I've written down here is an example of an entropic uncertainty relation. So you have the state psi, which is being measured in the basis Bi. So B1, B2, etc. are a set of bases. H Bi psi is the entropy of the output probability distribution obtained on measuring psi in the basis Bi. Now if I take the average entropy for some set of measurement bases B1, B2, B3, etc., then a lower bound on that is what constitutes an entropic uncertainty relation. The security of, for example, quantum key distribution and several other two-party protocols can actually be traced back to an entropic uncertainty relation of this form. And therefore, identifying bases which will saturate or which satisfy very tight entropic uncertainty relations becomes important from the context of quantum cryptography. So now let me proceed to talk about construction of mutually unbiased bases. So the construction that we will use heavily, we rely on heavily, is due to Schoom, Bandyopadhyay and collaborators. So the idea is to start with a set of d squared mutually orthogonal unitary operators for a d-dimensional system. So essentially we are starting with a unitary basis for the space of d cross d matrices. Now suppose there exists a partitioning of these D squared operators into what we call mutually disjoint maximal commuting classes, C1 through CL. So the size of each of these classes is D minus 1. So each class has D minus 1 operators such that the elements within each class commute, and they are mutually disjoint, meaning there are no common elements between any of the two classes. So for a D cross D space, one can show that if you would like to construct a maximal commuting set, then the maximum number of elements in such a set can only be at most D, including the identity operator. So a partitioning of these D squared operators into classes C1 through CL, which are maximal commuting classes and mutually disjoint. So if there exists such a partitioning, then the result of Bandyopadhyay et al. Tells us that the common eigenbases of such maximal commuting classes form mutually unbiased bases. So the common eigenbasis of C1 is mutually unbiased with respect to the common eigenbasis of C2, and so on. What more importantly, there's also a converse which holds true, which means that suppose we knew that there existed L mutually unbiased bases in D dimensions, then they show that there has to exist a set of L times D minus 1 such unitary operators which can be partitioned into L mutually disjoint maximal commuting classes. So this is a really nice connection between commuting classes of unitary operators and mutually unbiased bases, and in fact one can use this construction to show that in prime power dimensions one can explicitly construct D plus 1 mutually unbiased bases. So that's what I'm coming to next. So because we'll be working particularly with the n qubit systems, so consider a system of n qubits. Let Pn denote the set of all n qubit Pauli operators. Then what has been shown by several people is that there actually exists a partitioning of these Pauli operators into exactly D plus 1 mutually disjoint maximal commuting classes, and therefore there exist D plus 1 mutually unbiased bases. So all this has been rather abstract, I guess. So here's an example. Just consider a 2 qubit system. So we have 15 Paulis excluding the identity. Now it's easy, so what I've written down here is exactly a partitioning of the kind that I defined in the previous slide, namely each S1, S2, etc. are maximal commuting classes. They are mutually disjoint. So the common eigenbases form a set of 5 mutually unbiased bases in 4 dimensions. And of course this partitioning is not unique. So now I move on to our construction of unextendable sets also in for n qubit systems. So what do I mean by unextendable MUBs? So a set of MUBs that will be unextendable if there does not exist another basis that is unbiased with respect to this set. So there does not exist another basis in the Hilbert space that is unbiased with respect to B1 through Bm, then such a set is said to be unextendable. So one can, so we already have several examples of such unextendable sets. In particular, interestingly in dimension 6, so I told you earlier that the eigenbases of these generalized Paulis or the Weil-Heisenberg generators form are mutually unbiased. So it turns out that this set of 3 mutually unbiased bases is in fact unextendable, which means that one cannot use these to potentially construct a set of 7 MUBs in dimension 6. So the problem of trying to find complete sets in various dimensions is sort of closely related to this idea of unextendable sets of MUBs. Now one can define a stronger notion of unextendability. So if I have a set of bases such that there does not exist another vector which is unbiased with respect to them, then such a set is said to be strongly unextendable, and unfortunately this set is in fact known to be strongly unextendable. There does not exist another vector in 6 dimensions that is unbiased with respect to these the vectors in these bases. So now what we will need to use is unextendable sets of Pauli classes. So I have defined these maximal commuting sets of Pauli operators. So I showed you these examples in for the 2 qubit case. So what we had earlier here is what I would call a complete set a complete set of maximal commuting classes, because I have partitioned all 15 Paulis into maximal commuting classes, and that does not exist anymore. So this is a complete set of maximal commuting classes. But similar to how we define unextendable sets of MUBs, one could think of defining unextendable sets of Pauli classes, which means that I actually find a partitioning of these Paulis into, say, L classes, such that the remaining Paulis in fact cannot be grouped together to form a maximal commuting class. So a set of such classes is said to be unextendable, and our construction of unextendable sets essentially follows from the fact that such unextendable sets of Pauli classes exist. So I'll sort of elaborate on that a little bit. So here's an example. So consider this set of 3 maximal commuting classes. Now this contains only 9 Paulis, and we know there are 15, but the remaining 6 in this 2-qubit space cannot be grouped together to form a maximal commuting class. So there does not exist one more maximal commuting class that can be formed from the remaining Paulis in 4 dimensions. So here's an example of what I mean by an unextendable set of Pauli classes. So this is just what I just said, that you cannot find one more class of 3 commuting operators from the remaining 6. And it is sort of easy to see that the eigenbases of C1, C2 and C3, they are of course mutually unbiased. That just follows from the earlier results of Bandyopadhyay and others. But because these are unextendable sets, what that means is that the mutually unbiased bases that come out of these sets are also unextendable, but they are unextendable only in a weak sense, because what this implies is that you cannot find another basis, another mutually unbiased basis which comes out of a maximal commuting class of Paulis. So what this immediately gives rise to is a set of 3 weakly unextendable mutually unbiased bases. So I'm just formally defined this. So this one does not have to restrict oneself to Paulis. You can define this for any set of operators that are drawn from a unitary basis, a set of mutually orthogonal unitaries. So suppose there exist L maximal commuting classes of unitaries, then these bases that come out of these classes are weakly unextendable if there does not exist another basis which can be realized as a common eigenbasis of another maximal commuting class. So I'll just quickly run through our results now. So what we've shown is that given so in the process of going through our result, I'll also briefly touch upon our construction. So what we show is, given any 2 maximal commuting classes, C1, C2, there always exists a third class which I call C3 prime, such that the set C1, C2, C3 prime constitutes an unextendable set of maximal commuting Pauli classes. So how does this, how do we manage to show the existence of such sets? We start with C1, C2, then it is known that you can always generate a complete set of maximal commuting classes, but interestingly we observe a very interesting property of such classes. So from the operators in any 3 maximal commuting classes, we show that you can form exactly one more maximal commuting class, and this in fact turns out to be the C3 prime, which constitutes the third maximal class in our unextendable set. So C1, C2, C3 prime form an unextendable set. I'm sorry if I'm rushing through this, but that's because of lack of time. So if you want to talk about this in detail, we can discuss this construction in detail if you wish. So again, so like I said, the eigenbases of such classes form weakly unextendable sets of MUBs. We also show that, this is sort of a known result, that a set of 4 maximal commuting classes can always be extended to form 5 maximal commuting classes. So what this means is the number of classes in an unextendable set in dimension 4 is exactly 3. We have similar results for 3 qubits. But before I go to that, I would just like to quickly touch upon the 2 properties that I had mentioned. So one is, if I have an unextendable set of Pauli classes, then the operators in an unextendable set have this nice property that they can be repartitioned in this fashion. So what do I mean by that? So suppose, so this was the example that I wrote down earlier, C1, C2, C3. C1 is a maximal commuting class of Paulis. C2 and C3 are also maximal commuting class of Paulis. Now, observe that I can in fact form 3 more maximal commuting classes by picking one element each from each of these classes. So, follow the vertical lines, then YY, ZX and XZ is also a maximal commuting class, IY, XY, XI is also a maximal commuting class, and so on. So, I can repartition in a very symmetric way the operators in C1, C2, C3 into C1 prime, C2 prime and C3 prime, and this also constitutes an unextendable set of classes. Now, why is this property interesting? Well, this is interesting because in fact this set is exactly the set of operators which Mermin used in his original state-independent proof of the Cauchy-Specker theorem. So, our construction of, so we have a general way to obtain such unextendable sets, and we show that all unextendable sets have this nice repartitioning property, which means we now have several Mermin-like state-independent proofs of the Cauchy-Specker theorem. Unfortunately, I don't have time to explain to you what this state-independent proof is, but maybe if you're interested, we can talk about it offline. The other property, like I said, is saturating an uncertainty relation. So, the particular uncertainty relation that our set saturates is an uncertainty relation for the H2 entropy. H2 is the collision entropy, which I have just defined here. So, for 3 MUBs in 4 dimensions, so this is a well-known lower bound. This lower bound we show is actually saturated whenever B1, B2, B3 forms a weakly unextendable set of MUBs. So, we also show a similar construction for 3 qubits, where we show that the number of classes in an unextendable set is exactly 5. So, this of course immediately gives us weakly unextendable sets of 5 MUBs in dimension 8. And we also observe this nice repartitioning property in dimension 8, that every operator in this unextendable set can be realized as part of 2 different maximal commuting classes, which are in the language of contextuality. You say that each operator is now part of 2 different contexts, but the question of whether our the sets that we obtain in dimension 8 will in fact constitute a proof of the Cauchy-Specker theorem is still not clear, but because the repartitioning property alone is not enough to guarantee state-independent proofs of the Cauchy-Specker theorem. So, we have numerical example to show that some of the unextendable sets that we construct are in fact strongly unextendable, which means there does not exist even a single vector that is unbiased with respect to these sets. We also have numerical evidence to show that our construction can in fact holds even in higher dimensions, but we do not yet have a general proof of this construction for any 2 to the n, but of course we have some idea of what the number of such unextendable of classes in such unextendable sets would be. So, with this I conclude. So, what we have shown is the existence of small unextendable sets of Pauli classes in dimensions 4 and 8. These are of course dimensions where complete sets exist, but we show that in fact there also exist these unextendable sets, some of them which can in fact be strongly unextendable. So, this leads to weakly unextendable sets of MUBs, and some of these examples are in fact strongly unextendable. We provide explicit constructions in 4 and 8, and we conjecture the existence of such incomplete unextendable sets in higher dimensions as well. And our construction simply relies on the properties of these Pauli operators. In particular, it relies on properties of a partitioning of a complete, it relies on the properties of the complete set of maximal commuting classes, and these properties in fact hold not just for Paulis in 2 to the n, but if you think of these generalized Paulis in higher prime powers, then these properties also hold for those. So, our construction could potentially be extended very easily, at least to the case of just prime power dimensions. And finally, we show that these unextendable sets have some interesting properties which might make them useful. So, the complete set is of course very useful, is useful for tomography. Incomplete sets not so much, but it seems that they can find other applications and might therefore be worth looking into some more. Thank you.
We have some questions.
So this is unextendable Pauli basis, right?
Yeah. Yeah.
Have you thought of, so the extension you are restricting into the Pauli basis itself, right?
Yes, yes.
So what happens if you don't restrict into that?
Yeah, we have not actually looked into that, which is why we don't claim that these are unextendable sets of MUBs. They are only weakly unextendable, in the sense that you cannot find another basis which is a common eigenbasis of a set of Pauli operators. But yeah, we have not been able to extend this beyond that. Probably with the affirmative of your statement. Yeah. Sorry?
Hello. So you have conjectured that
Yeah.
existence of unextendable
Yeah.
sets of d by 2 plus 1.
Yeah.
Is that upper bound or is it known?
We don't know it. We don't know. So we have numerical evidence which shows that that is in fact an upper bound, that there do exist some smaller sets in, say, for 5 qubits. Numerical evidence suggests that this is in fact an upper bound.
Okay.
Yeah.
If you take all maximal commuting subsets, then these systems will overlap, and that is the reason why we are not able to extend the systems. So with Shivashish Ghosh, we have worked out maximal commuting subsets families for various systems, and we call them fans because they either look like Japanese fans or round fans. And we have characterizations of unitary equivalence of various unitary bases.
Yeah, so yeah, it would be interesting to see what happens in higher dimensions. So you have this fan structure in a discrete, when you
Yes.
draw these things in a discrete phase
Right,
space.
you are right.
Yeah,
Thank you.
that would be interesting to look at.
Thank you.
Okay, any more questions? If not, let's thank Farva again, and we'll have some announcement about lunch and the rest of the day.
Thank you.